show up very well sometimes, but yeah, it's not a very good recorder. Pretty much picks up my voice only, which is great fun. So I'm standing right here, yeah. So nonlinear function is a function whose graph is not a line. These are examples right here of linear functions, and then on the bottom, nonlinear functions. So you kind of have a picture in your mind of linear versus nonlinear, hopefully. Linear makes a line, nonlinear does not. So it says classifying a function as linear or nonlinear. We're going to classify it by just graphing it and seeing if the dots line up or not. So the area in square inches of a pizza is a function of its radius r in inches. The cost, C in dollars, of the sauce over here is a function of the weight W in ounces of sauce used. Graph these functions shown by the tables below. Is each linear or nonlinear? So one of these will be nonlinear, one is linear. So here we have the area. Remember, area is two-dimensional. Area is two-dimensional, whereas like perimeter was one-dimensional. All of our problems yesterday were perimeter. They were one-dimensional and they were linear. Something to keep in mind here. So go 2 over up to about 12.57. We'll just do our very best to estimate where that dot would be. So go ahead and do that. 4 over and it's about at 50. And then 6 over and I'm about at 113. So just do your best to estimate it. Already with 3 points you can see that it is not linear. It seems to be curving. Over at 8 it's up at about 201, so about 200. And then 10 it's up at 314. So you can see it starts to curve. If I were to connect those dots, it's definitely nonlinear. It's actually the right half of what we call a quadratic function. So that's an example of a nonlinear one. And so when I ask you to do this in the classwork, it'll be pretty obvious when you start graphing it. I have the graphs on there for you. So I've scaled it and everything. Okay. So as you start plotting the points, you should be able to tell linear versus nonlinear. Okay. What about this one? We got 2 and then 80 cents. So 2 and 0.8. And we've got 4 and $1.60. And we've got 6 and 2.40. I kind of already know this is, yeah.
Because it goes up by 80 cents.
Yeah, so you can see me carefully lining up the dots, right? But it does. It goes up by 80 cents each time. You can see it right here. It's up by 0.80. It goes up by 0.80 here. So yeah, it is a little tricky on some of these with these scales. But then at 8, it's at 3.20. And then at 10, it's at $4. There it is. So this one is definitely linear. Don't even really need a graph to see that. And we could come up with an equation for it too. You guys could figure one out if we're asked to. We're going to be asked to do that on some of these as well. That's the hardest part of this lesson, is finding the equations for the nonlinear function. So just plot those points, mark that it's linear. Now you try. The table below shows the fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Graph the function represented by the table. Is it linear or nonlinear? Why don't you go ahead and plot these points, and then let me know if you think this is linear or nonlinear. So plot the points. Let me know if it's linear or nonlinear. So as we plot them, remember these are the x's up here, and these are the y's. It should be coming down, actually curving down. So is this linear or nonlinear? Nonlinear. Look at what we're talking about here. area. What dimension is area? We calculate the area of a carpet here. You have two dimensions, right? A length and a width. So linear means one-dimensional, like fencing or perimeter. Okay, so as soon as you see this word area, it's two-dimensional. That's nonlinear. So it's kind of a dead giveaway. But yeah, nonlinear. Will the area ever reach zero? This is interesting too. It's like if I play golf and I only hit it halfway to the hole each time, will I ever get there?
No.
Theoretically, no, right? Eventually, it's like I can't hit it. Yeah, halfway there anymore, it'll just fall into the cup. Yeah, like the.
Well,
right, but theoretically, I'd never get there if I only hit it halfway there each time. So, will the area ever reach zero? No. No.
what do you mean you'll never get it in the cup?
Well, I will, but theoretically, I could never get it there if I only hit the golf ball halfway to the hole each time. It's just like with this
But
area.
it only takes 2 times, halfway in there.
No, I go
So it's
half
halfway in
of
the
what's
cup.
left. It's half of what's left.
Keep going halfway.
You would never get there.
So no, it would continue
Like in real life, you could.
to cut area
Oh, in math
In
just
half.
cuts us all off. Doing fun things. So
and never reach zero. All right. Here, this one they tell us, guys. They tell us this is a nonlinear function. This is okay. We talked about area is two-dimensional. What dimension is volume? So volume of this room. Yeah, because we've got length, width, and then height. So if area gives us an equation with an x squared in it, then volume would give us an equation with an x. It's actually cubed is what we call it. Good. So here's how this works. It says the table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. So it says number of blocks on an edge is 4. So if you picture my Christmas puzzle over here, it's 4 by 4 by 4. What's 4 times 4 times 4 equal? 64. 64.
We are 60.
What's 5 times 5 times 5? I had a 5 by 5 by 5 cube. 125, yeah. So here are my ordered pairs. I've got 4, 64, 5, 125. Let's go ahead and graph this thing. So at 1, 1 is, I don't know, somewhere right around here. 1, 1. And then it has 2, 8. So it starts off kind of slow. 327. And it's going to take off here. 4, 64. And then 5, 125. Looks kind of like the one I just did, except that this cubic, it's called a cubic equation. It's actually, if I write the equation down, it's y equals, and you're going to need to recognize these cubic numbers. I'm going to circle them here. 1, 8, 27, 64, 125. It's going to show up in your classwork. The equation is y equals x to the third. You just have to recognize that. Okay? You have to recognize those cubics. You have to understand, in the real world, that volume is 3-dimensional. So there should be a third power somewhere in your equation. Okay. So you need to recognize these numbers. You need to study those. But y equals x cubed. What's happening here in words is you're multiplying the edge by itself 3 times, right? And it's very non-linear, so it grows very quickly. It kind of looks like the x squared one, the one that we did with the pizza area, but this grows faster. Take for an example here. If I square 1, I'm still at 1, right? If I cube 1, I'm still at 1. But then I move to 2. I square 2, I'm at 4. If I cube 2, I'm already at 2 times 2 times 2 is 8, yeah. Plus students will say 6, but it's 2 times 2 times, we see this easy to do. 2 times 2 times 2 is 8, yes. So it grows faster when it's x cubed than x squared. Okay. Now you try. This is a little different equation. I'm not going to have you try. I'm going to actually go through this with you because this is different than x cubed. It says the table shows the number of new branches in each figure of the pattern below. You've probably seen this in other classes or some, things like this. What is a pattern you can use to complete the table? What's happening here? So here it splits into 3, and then here each of those branches splits into 3, and then here each of those branches splits into 3. So what's happening as we go from here to here? I'm multiplying by 3. So I'm going to take the 27 and multiply it by 3 times 3, and I'm going to get 81. And I'm going to take that times 3, and I get 243. Good. 243. So this is actually called a geometric sequence in math. The previous term, or we could say the number of branches, gets multiplied or triples each time. We'll say the number of branches gets multiplied by 3 each time. So instead of having a common difference or going up or adding 3 each time, it's getting multiplied by 3 each time. So the question is, what is the equation for something like that? This is called an exponential equation. It looks like this. It's y equals, the base is 3, and the power is the variable. It's 3 to the x power. Here's what that means. If I plug in 1, 3 to the first equals 3. 3 to the first equals 3. If I plug in 2, 3 to the second equals 3 times 3, or 9. See how I got the 9 there? 3 to the third equals 3 times 3 times 3, which equals 27, and the pattern continues. 3 to the fourth, 3 times 3 times 3 times 3, which equals 81. 3 to the fifth, just keeps going. 3 to the fifth is 3 times 3 times 3 times 3 times 3, which equals 243. Okay? So that is called an exponential pattern. So you'll have to watch for that. When you see this word multiplied by a certain number each time, that number becomes the base of the exponential function. So you might want to put a little arrow there. That multiplier is the base. So my graph would look like this. It grows very quickly. At 1 I'm at 3, somewhere down here. And then at 2 I'm at 9. Starts off kind of slow. And then at 3, here it goes, 27. 4 I'm at 81. 5 I'm way up at 243. So it just takes off like crazy. So you can see if you were to draw the curve in here, it gets steep really fast. So that's called an exponential function. So one of those will show up on the classwork. Okay, so just have to recognize it. It'll go up by multiples of 3 or something like that. I think it's actually the same as this one, so watch for it. Give you a chance to graph that. Exponential growth. What kinds of things in life grow exponentially? Yeah, at least in the beginning, and then they level out. People probably do in the beginning, and then slow down. Money can grow exponentially. Sometimes it'll go up and down, but it can, actually. All right. Writing a rule to describe a nonlinear function. So I'm going to give you just some ordered pairs like this. I don't give you the table. You might want to put it in a table. It would go like this. 1, 2, 2, 4, 3, 8. You see how I'm getting the numbers in the x's and y's? First number is the x, second number is the y. So then we got 4, 16, and then 532. And then we are going to come up with a rule that represents that function. First of all, is there a constant difference here? Difference here is 2. Difference here is 4. Not constant then. So is it linear? No, definitely not linear. This is similar to the pattern I just showed you. What's the common multiplier? That's the next thing. So ask, is there a common difference? The answer is no. No. So it's not linear. Second thing you might want to ask before you just start, you have to have like cubics and squared ones memorized, but is there a common multiplier? Yeah. What's wrong there? Is there a common multiplier? Yeah, it's 2. So yes, it's 2. And so you can see from here to here, from here to here, here to here, here to here, we're doubling. So this is just like the equation I just did, except instead of a 3 to the x, it's a 2 to the x equation. So when you have a constant multiplier, that's how it works. This could show up in your classwork today. You have to look at the y coordinates and find out what the constant multiplier is. That becomes the base. Okay, the constant multiplier is the base, and then it has a power of x. Okay, so it could go up by 2 or 3 or maybe 4. It probably won't be any bigger than that. Okay. So if you see that there's a constant multiplier, that's the equation. If you see numbers like 1, 8, 27, 81, those numbers, that's a cubic, x cubed. This one should be one I think you'll recognize. It says, what's the rule for this? 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. Do you recognize these numbers as I go down here? 1, 4, 9. Yes. Not quite all the way down, because if I multiply 4 times 4, I get 16. But that's like it skips to get there. Special numbers. One is 1 squared. 4 is 2 squared. 9 is 3 squared. See it? We got 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. What's staying the same? The squared. What's changing? What's the variable? The base, the number. So this is y equals x squared. Okay, y equals x squared. You're going to need to be able to recognize these numbers. It will show up on the classwork. All right. Any questions on this so far? So we've got equations like x cubed, x squared, 3 to the x, 2 to the x. You might want to, in your section summary, write something like this. The numbers 1, 4, 9, 16, 25, that's a y equals x squared pattern. Maybe write that down. That's something you should memorize. Do you remember what the cubic pattern was? It was 1. What's 2 cubed? 8. 3 cubed was 27. 4 cubed was 64. 5 cubed was 125. You won't see it go above that. That's the y equals x cubed pattern. You might want to write something along if there's a common multiplier. If there's a common multiplier of 2, then you have an equation y equals 2 to the x. What if there's a common multiplier of 3? What would that nonlinear function equation be?
X equals 3. 3 to the x. 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 3 to the x.
be y equals 3 to the x. So probably a lot of new things in this that you might want to jot down in that section summary. So you can go ahead and start on the classwork. You have about 6 more minutes on it. I'm going to assign this for homework too. Do not do the homework yet. Okay, we'll do that in class tomorrow. We're going to work on that together with my guidance. I'd like you to try these. In the classwork, you'll find each one of these nonlinear functions will show up. You just have to recognize it. Okay, so use your notes. Yes, do all the classwork.